So section 6.3, I'm not going to be testing you on a lot of the stuff for this in this section. There's not going to be a direct quiz on this stuff, but this builds up towards section 6.4. And in section 6.4, there's going to be a lot of stuff. But the overall theme is this, that X bar, your sample mean, is a random variable. Just that simple. X bar, your sample mean, is a random variable. Now let's explain that a little bit, because maybe that doesn't make complete sense right now. Let's take a look at the heights of a pro basketball team, just really hypothetical, just the starting 5. So these 5 down here. And it's probably not that hard of a stretch to calculate their average height. And you can do that. It would be the mean, so mu in this case. Why am I using mu and not X bar? Because you got all the data. This is the population parameter. It's not a sample statistic. So mu, the average height here of people on this team, is 80. Now typically you don't deal with a population this small. Usually you have a huge population and you don't know what this number is. So the best that you can do is try and take a sample and hope that your sample estimate gives you a good estimate of this. So let's consider taking samples from this population. Suppose I'm particularly lazy. I don't want to calculate the mean for all these. I'm just going to look at the heights of 2 people. I'm going to take 2 people out of this population at random. So my first question to you, since order doesn't matter, how many ways are there to choose 2 people from a group of 5? Take out your calculator or your favorite technology and remind yourself, refresh your memory, because you've got a test on this a week from today. How do you find 5 choose 2, or combinations of 5 people or 2 people chosen from a group of 5? Do that calculation. So let's just open up a new sheet here. As a reminder, you start typing in combinations, and it doesn't get too far before it says, oh, you want this? Sure. 5 comma 2 gives me 10. You should be able to get that there's 10 different ways you can choose a group of size 2 out of this group of size 5. So let's put that 10 up here. And here's those 10 different possibilities. Now keep in mind, I'm choosing these as a sample so I can try and get an estimate of the true population mean. How did I do? Well, 77, not so bad. 77.5, a little bit better. This one's a little bit too high. This one's spot on. And these last 2 are pretty high, all right? But that's okay. These are just estimates of my sample mean. If I total up these sample means, then I can calculate their average. Remember, the average is calculated as the sum of your data divided by n. In our case, we had 10 pieces of information. What was the sum? Oh, it was 800. What's 800 divided by 10? Somebody without their calculator. 80. And what's that saying, interestingly enough, is that even though these aren't always right, in fact, it's only exactly right once, on average, they give me the right answer. Because the mean of these samples, mean of those sample means, is actually 80. It matches this number over here. And that's good. That makes this what's called an unbiased estimator. And I'll talk more in depth about that in a little bit. But maybe I started getting a little burst of energy. Maybe I said, you know what, let's bump it up to samples of size 3. How many samples of size 3 are there from a population of 5? 10 again. And that's interesting that they're symmetric, but if you think about it, choosing the 2 that you want is like choosing the 3 that you don't want, right? You're just leaving them off. So these 2 numbers should be the same. You get different means but kind of a similar result. If I add up all these sample means, keep in mind that these are all estimates of this. If I add up all those sample means and calculate its mean, I'm again going to get 880. On average, the sample mean is giving me this. And that's good. That makes this an unbiased estimator. And let's watch what's happening. Here's my original population. When I take samples of size 2, I get all these are different estimates of my population mean. I don't know what the population mean is, typically, but all these different points are trying to estimate the population mean, which is our mu. Mu equals 80. So there's some that are close, some that aren't so good. But then we're going to bump things up to a sample size of 3 and start looking at this in the case when we have 3 as our sample size. And we get these estimates. Now, one of these is actually spot on. That's fine. That's interesting. But the rest of them are kind of scattered around. You know, some are good, some are bad. I wouldn't say necessarily bad, but some aren't so great. Let's keep going, though, up to samples of size 4. This is going to be that last one down here. How many samples of size 4 are there?
5.
There's 5. Basically, choosing 4 out of 5 here really means you're choosing the one you leave out. And there's 5 different choices about the one that you leave out. If you calculate the average of these, once again, you're getting 80. So this number consistently matches this number. We don't know which one of these is right, if any of them is right, but on average, by using this, on average, we're getting the right number. So there's our samples of size 4. Let's look at these. And something's happening when we increase the sample size. What's decreasing? The standard deviation. The spread of our data is decreasing. So that's actually one of the conclusions that I want you to get out of this. As the sample size increases, the standard deviation of this random variable, x bar, decreases. You can see it visually. Take a look at the spread of the data here, the spread of the data here, and the spread of the data here. As your sample size increases, you're going to get a better and better estimate of what that true population mean is. And that's good because you're sampling because you want to know this. You want to know, well, what's the average height? Going back to this, all these values, they're going to be by chance. It's going to be who ends up in your survey. That value is going to be determined by chance. So one of the big things about this is that x bar is a random variable. The other conclusion that we got out of this was that the mean of this random variable is the same as the mean of our population. Sometimes I'll call this the parent population, not anything to do with my last name, but because that's what gave rise to this sample. That's where you sampled from. All right, let's take a pause from this and look at some actual numbers here. So if you take the time to open up this link from D2L, it should direct you to here. This is the second of the 2 links I put up there. Is this one opening up okay for you guys? Okay. You've got various different sets of data. You got sleep 1, sleep 2, and sleep 3. I don't know what the data represents there, and it doesn't really matter. So what I want you to do is I want you to click sampling options. It should give you a little something like this over here. And let me set in a few numbers here for us. Let's keep the number of samples as 2,000. There's 18,000 pieces of data in this data set altogether. We're going to draw them out in samples of size, say 9. So what's going to happen here? It's going to take and randomly select 9 samples from this data set of 18,000. And then it's going to calculate the sample mean for that one sample. That becomes one observation in our new data set. We'll do that 2,000 times. Actually, we'll let the computer do that 2,000 times. And then we'll plot its mean and standard deviation. We'll do a histogram. We'll see how it compares to our data. Here's your regular data set. It goes from about 2 up to 13 hours of sleep. Man, that's awesome. That's like 2 days worth of sleep. That's excellent. In any case, let's draw our samples. There we go. Now the overall mean from our raw data was 8.001. What was the mean of our sampled data? Yeah. Really close to what we started out with, right? That matches what we concluded on our handout. That on average, this random variable has the same mean as our population mean. So we started out with a population mean of 8.001, and our random samples ended up with a mean of 7.998. Now yours might have been different, right? Did you guys get slightly different numbers? Yeah. That's okay. But they're probably very, very similar. The mean is near 8, the standard deviation is near 1/2. Let's change our sample size. What happened when we changed our sample size last time? Well, something shrunk, right? So the standard deviation shrunk. I'm going to make a prediction. Even though I'm not working on your computer, let's change our sample size to sample size of 25. My prediction is that when we do samples of size 25, your mean is still going to be close to 25, but the standard deviation is now going to be close to 0.3. So let's find out if I'm a modern day Nostradamus or not. Draw our samples. Oh, that's pretty good on that one. 0.302. What'd you guys get? What were some of the numbers you got? 0.301? 0.303? Okay. So what I'm hearing is that I was right. All right. Let's do it one more time. Let's go up to samples of size, say, 100. Now I think that your standard deviation is going to be down to about 0.15. Let's draw our samples. Not bad again. Wow. I should go play the Super Lotto, right? All right. Now, has the standard deviation decreased by that much? Sure. Take a look at the distribution of these sample means. So what it's doing is that for each time it draws a sample of size 100, it's calculating the mean of that sample. It does that 2,000 times, and here are the results. But look at how tightly they're clustered. Our data here goes from 7.5 to 8.4, whereas originally went from like 2 to 13 or 14, somewhere in there. So it's much more tightly clustered than it was originally. That's a predictable trend. We're going to see that as you sample. The good news is that what it's saying in its own way is that the more you sample, the more certain you are about your sample estimate. Remember, we're sampling here because we want to get an estimate of this population. If the standard deviation is decreasing, that means samples based off of a larger sample size are more likely to be close to the true population mean than samples based on a smaller sample size. Here, well, With samples of size 2, you're not necessarily going to get very close to the actual population mean of 80. Whereas with samples of size 4, you're likely to be very close to the correct population mean. All right. Let's flip things over to the back side. This is building towards section 6.4. We're going to start out with 3 distributions. One's a normal distribution, one's a reverse J, and the other one is uniform. It doesn't really matter so much what type of distribution you start out with. Something similar happens when you keep sampling from it. So if you take samples of size 2 and calculate the mean, then the sample mean will have this distribution, or this distribution, or this one, depending on which population you started out with. And then you jump up to samples of size 10, and finally samples of size 30. And by the time you get to a sample of size 30, what do you notice about all these distributions? Yes, they're skinnier and they all look normal. Both conclusions are spot on and important. So well done on that. What that's saying, and what I've been trying to hint at all along, is that for this random variable, there's 2 conditions under which this random variable is going to have either a normal distribution or an approximately normal distribution. So X bar is a random variable. Not sure if I'll put it on the test or not, but I used to have a question that said, complete the sentence. X bar has blank. And then your answer would be, an approximate normal distribution if the sample size is large enough. That is, if the sample size is greater than 30, then it's going to have an approximate normal distribution. That's really useful. It's incredibly useful. And it's amazing that it happens for a variety of things. It doesn't just depend on starting out with a normal distribution. If you start out with a normal distribution, all your samples are going to have a normal distribution. If you don't start out with a normal distribution, then for samples of size 30, X bar has an approximate normal distribution. So there's 2 ways under which X bar is going to have a normal or approximately normal distribution. If you're sampling from a normal population, then X bar is going to have a normal distribution. It's nice. It's a very, very nice property. This is the big theorem for this course. In calculus, you have the fundamental theorem of calculus. In algebra, you have the fundamental theorem of algebra. But here, we've got what's called the central limit theorem. And that is, for a large enough sample size, X bar has an at least approximate normal distribution. That's really handy. All right. Not sure we want to do too much. Oh, there's one last thing I got to mention in association with this. I mentioned biased and unbiased estimators. So let's see here. An unbiased estimator is a statistic that, on average, correctly estimates its population parameter. So let me remind you of some of our statistics. So this is an unbiased estimator. And I'll inform you about which statistics are unbiased estimators and which ones aren't. So let's start out with the mean. Does anyone remember what the notation is for the sample mean, your statistic? Ooh, that would be X bar. What's the corresponding population parameter? Mu. For the variance, that's going to be S squared, and the parameter is going to be sigma squared. How about for the standard deviation? Nice. S and sigma. When we're working with statistics, we hope that our statistic gives us a good estimate of our population parameter. We often don't have these values because that would mean you have to calculate, you have to take a census of everybody in your population. That might be impractical or in some cases impossible. So let me give you a list of unbiased estimators and biased estimators. And let's gain some insight into this by looking back at our sheet here. Let's see, this one right here. Do you remember what the range is, the range of a set of data? Thank you, Edmund. Highest minus the lowest. So what's the range for this one? Range of this population worth of data? Yeah, 86 minus 76 is 10. Let's take a look at the sample range for all of these. So the range is the top minus the bottom. Well, if our sample only consists of these two, that would be a 2, that'd be a 3, a 5, a 10, a 1, a 3, 8, 2, 7, and 5. Let's see what the average estimate of our sample range is. So let's see, that's going to be 10, 21. Let's see, that was a, that's a, no, it's an 8. All right, let me go back. 21 plus 3, 24, 32, and 14, 46. So the total of this is 46. If there's 10 observations in this, what's the average sample range? 4.6. Now when we're dealing with the mean, the average value of the mean was 80. Is the average value of the sample range, does that equal 10? No, not even close. So the sample range is what's called a biased estimator of the actual range. This is always going to be lower than this. So in terms of biased estimators, one of them would be the range. Unbiased estimator would include the mean. Biased estimator would include, well, let's see, let me do the unbiased one first. The variance is an unbiased estimator. Interestingly enough, even though all you're doing is you're taking the square root, the standard deviation is a biased estimator. Not by a lot, but by a little. Finally, another one, the population proportion, or proportion. Yeah, let's try that again. So the proportion, that's a good estimator of your population proportion. It seems to me there's one more here. Range, I think the median is a bias estimator. On that one, I'm not 100% sure, but I think the median is a biased estimator. So those are your unbiased and biased estimators. You don't have to have a complete understanding about those, but what I want you to understand is that an unbiased estimator, on average, equals its population parameter. A bias estimator, on average, is not going to equal its population parameter. That's the difference between those two. Comments or thoughts on this last little bit? Yes, Cosmo? It's kind of goes back to the central limit theorem is what I mentioned here. We'll talk a little bit more about that next time in association with our work for section 6.4. Our work in section 6.4 is going to be all about using these new distributions that we get from sampling from a parent population. Anything else? Have a good one and see ya!